Oh, hello. Just excuse me whilst I finish this off. There we go. Of course, you don't usually see a picture of me like this. It's more like this. That's better, yes, I'm here. This is an ordinary picture made from ordinary light and produced by an ordinary television camera. But this camera doesn't need light. It produces pictures by heat. It uses infrared that our eyes can't see into a television picture that we can see. So if we turn the ordinary lights off again, the different brightnesses show different degrees of heat. Now, the hottest parts are white, like my face and like, well, like the teapot here. And watch what happens if I pour out another cup of tea. This is a cold cup, and I'm pouring in the hot tea. In fact, you can see the stream of hot tea, white, going down there. Now, you'll watch the effect as the cup heats up. It slowly gets brighter. And in fact, I can show you another effect. If I put the tea cosy over the teapot, that stops the camera seeing the heat in the teapot because that doesn't let heat through. And consequently, the teapot gets darker. So the blacker parts of the picture are colder. The infrared camera is being worked by Station Commander Paul Quick from the London Fire Brigade. Hi, Paul.
Hello.
So, Paul, what do you usually use your camera for?
Camera in the conditions we work in. That's normally darkness and smoke. And the camera enables us to see warm bodies, furniture, and whatever is in that building.
So, in fact, this camera can help save lives.
Undoubtedly.
Yeah. How sensitive is it, then?
The camera itself is very sensitive. Perhaps we can demonstrate the camera with this piece of timber.
Yeah.
Now, if I put the camera at that piece of timber, you can just about see it.
Ah, yes, you can see it's that big black square because the wood's obviously cold. So
That's
it
right.
comes out dark, yeah?
That's right. Now, if I ask you to put your hand on that piece of timber,
Yeah.
just for a few seconds, and now remove it.
Yeah. Oh, wow, look at that. Oh, yeah, what is that we're looking at there?
That's the heat from your hand retained in the wood,
Yeah.
and the camera then picks up the heat.
So, just where my hands warm the wood up, that very small temperature change shows on the camera. Let's try again. Oh, yeah, just those little fingerprints there. That's fantastic. That is something else. I mean, that picture is obviously one that we wouldn't normally see. The camera has artificially extended our visual sense. But not only can we make pictures from heat like this, we can also make them from sound. Take a look at this.
Okay, so looking at the first baby, see the head, the face, see the hand moving up to the face. And if we look at the chest, see the heart beating there in the chest, see the flicker. Again, the head, the heart, and there's the hand. So that's one healthy looking baby there. If I move the transducer, let's go up for the other baby. There we are, there's the other baby here. You can see the head there. Not quite so clear to see because of the position. If we just go back to the first baby, we can see that a little clearer. You can see the spine here. See the two parallel lines. It's the spine, it's the bottom line we're interested in. If there's anything wrong with this, that's where we find the defect. That looks nice and normal.
This machine is using sound waves to make pictures. The sound is so high-pitched that we can't hear it. It's called ultrasound.
See that?
He's right underneath the other one.
See, punching him. See that on there? A couple of prize fighters there.
Well, it was easy enough to tell that that was a picture of a baby. Once somebody had pointed out the arms, the legs, the head and so on. Once an expert had helped us. But what about this picture? Let's zoom in. Now, what could that be? Any idea? Right, Bill, you're the expert. Can you give us some clues as to what that might be?
Well, the machine's producing pulses of ultrasound, which are being reflected from the front surfaces of these circular structures. And we can see they're about 1.5 centimetres, 2 centimetres wide. And we can see they're grouped quite closely.
Let's see what it is then.
There we have...
A bunch of grapes. How did you get this picture then?
If we look at the transducer, the ultrasound transducer, against the screen, the transducer actually produces a pulse of ultrasound, which is driven across the screen in the sector, echoes return to the transducer, thereby giving us the ultrasound image.
So as the waves go backwards and forwards across here, they're bouncing off anything underneath to give you the picture. But of course they're not bouncing off my fingers. That's presumably because it doesn't work in air.
Exactly. We need to scan through some kind of fluid, whether it's a gel, whether it's a water bath.
The very high-pitched pulses of sound are in such a thin beam that as they pass through, they make a picture across the womb.
Let's go back in. This baby's jumping around. Football in
One
there.
of them was
If you want to see something small, you might hold it closer to your eyes. But if you hold it too close, everything's blurred and the eyes can't cope. But there is an instrument which can improve your eyesight. That's a microscope. They can vary from this quite fancy one here to a simple magnifying glass. Either way, they open up a whole new world. And this is Dr. Stephen Carter from the Buxton Micrarium to help us explore that world. Hello, Stephen.
Hello, Terry.
What's a micrarium?
Well, I think the easiest way to explain the idea behind a micrarium is to compare it with a planetarium. The planetarium displays the wonders of outer space as revealed by the telescope, and we go to the other end of the scale and invite our visitors to explore the wonders of inner space as shown through the microscope. What perhaps is not too obvious to everybody is that the world of inner space is, to an explorer, every bit as vast and as fascinating as the world of outer space.
Well, to help us see that area, we've rigged up a television camera to your microscope here, and we can see it on the screen. So what have you got for us to see first?
Well, this is something which is very common. Everybody has seen it sometime or another, but very few people really look at it carefully.
Well, to me it looks like a pile of sticks and stones.
It is, in fact, a little sample of sand from the beach.
Goodness, what are those long sort of stick-like
These
shapes?
green and purple shapes, they're
Yes.
rather pretty, aren't they?
Yes.
Those are tiny fragments of sea urchin spines that have been ground up by the action of the waves and then bleached in the sun to this rather attractive colour.
Now, it's all a lot bigger under the microscope, isn't it? How much
Yes.
bigger?
Looking down this microscope, you see things about 20 times bigger.
So that meant something as size of an apple, perhaps, would be about that big, wouldn't it, under the
That's
microscope?
right, yes.
And as long as we could fit it under the microscope, you'd be able to see the surface area in a lot more detail,
That's
wouldn't
correct,
it?
yes.
But you don't need anything quite so expensive as this microscope. You can actually use a microscope similar to this one here. Right, what else can we have a look at?
Well, here is a little clump of moss. Can you see that?
Well, that's like walking through a jungle, isn't it?
It is very much like a jungle. In fact, it's a microscopical jungle, and within that jungle there are all sorts of strange and unfamiliar animals and plants.
It's glistening a lot. There's obviously a lot of water on it.
Yes, on each leaf there is a thin layer of water which is causing that glistening, and in fact it is within that layer that many of these fascinating animals live.
But we couldn't see any of those animals using this sort of microscope, could we?
Not very easily. If we want to look at those more carefully, we need to use a microscope that we have over here.
So first you have to get the water out of the moss, don't you?
And how we do that is, first of all, we must start with the moss very moist. If you don't collect it moist, then it needs to be soaked in water for, say, a couple of days to revive the animals that have been dried out. Then all you need to do is to put it in a plastic bag like that and squeeze the water out into a beaker like this.
Yes, pretty dirty it looks too.
Then we're going to make a slide to put that water in, and I've already put a piece of tape, adhesive tape, on this microscope slide with a cutout area which I'm now going to peel off. And we now put a microscope cover slip over that cutout area and simply tack it in position with two little pieces of adhesive tape. One will do there, and one there.
So you've made a very thin space underneath that glass.
That's
now,
right.
haven't you?
And we can run the water from the moss into that space by drawing some up with a fine pipette and simply allowing it to run under the cover glass like that.
Right, let's have a look at it.
There we see what we've got.
So what's this brown one here then?
Well, the brown part is a special case that the animal has made. It's like a sort of vase. And originally it was attached to a moss leaf by the base there. But of course we've detached it by squeezing the moss. And a little animal that lives in there is now poking its head out, and you see it is creating a current. And those are all particles of food streaming towards it.
Yes, everything's moving in the direction.
That's right. If something too big hits it, it will disappear inside that little protective case.
Now, what's that thing with wheels there?
You say it's got wheels. In fact, that's an optical illusion. But early naturalists did, in fact, refer to them as wheels. And they are two little lobes at the front end of the animal, which is called a rotifer, a wheel bearer. And hairs on those lobes are beating in a circle in perfect synchrony. You see them there?
Yeah.
And creating a current in the water which draws the food towards it. Do you see those two things behind the head which appear to be gnashing together? Those are in fact the jaws, well back from the front of the animal, which are crushing the particles of food that are accepted. You see one going down the gullet then?
So it's pulling in the particles and they go
Yes,
down
you can see them past the body, can't you?
Yes, and then being chewed inside there.
That's right.
Now, that was just using ordinary light, wasn't it? But there are some tricks that you can do with a microscope, aren't there?
Yes, and let's try one of those tricks using these crystals that you can get from the chemist. Now, I'm going to be handling these, so I'm going to put on a pair of gloves and some goggles, because you can't be too careful with handling any kind of chemical.
Right, this is paradichlorobenzene moth crystals. Now, how are you going to get one of those underneath the microscope?
Well, what we're going to do is to take a microscope slide and select one of these crystals, quite a small crystal will do, put it on the slide like that, cover it with a microscope cover glass, and then put it on the hot plate, because these crystals melt at quite a low temperature.
Right, it looks like it's starting to go there.
Right.
Now that's ready to go onto the microscope, is it?
No, not quite. I think we ought to put it aside to let it cool and let the crystals reform.
Yes.
But I put this preparation already under the microscope, so let's take a look at that.
Well, I must admit that looks a bit boring to me.
Ah, yes, but now see what happens when I do this.
Oh, that's stunning. That is beautiful, isn't it? And you've got that effect by using polarised light, haven't
Right.
you? Now, we used polarised sunglasses, but I can't see how you get the effect.
All right, try turning one of those glasses until it goes black.
Right, there, black, nothing. I see how I see blackness, but now I can't understand how you see the crystals.
Well, let's see what happens when we put some crystals between those two lenses and turn them round.
Ah, bright colours, what's happening?
What is happening now is that the crystals have the effect of twisting the light.
And give us those amazing patterns.
Right.
Right, now you have got polarised filters fitted in to that microscope, haven't you?
Yes.
But if you haven't got that on a microscope, can you use this sort of thing to get the same effect?
Certainly. All you have to remember is to put one of those filters below the level of the crystals and one of them somewhere above the level of the crystals, and arrange so that you can rotate one of them until you get the effect that we've seen.
Now, you have one more thing you can show us, don't you?
Yes. What I want to show you is these crystals actually growing. And in order to do that, I'll put this back on the hot plate, but only half of it, so that it's overlapping the edge of the hot plate like that. Half of those crystals have now melted. I've got to put it back on the microscope, and with luck, we will see it's still melting at this stage.
Right.
That margin is now retreating, but when it's cooled down a little bit further, you'll see the crystals beginning to grow.
There they go. That's
And
beautiful.
they get slowly faster, they get progressively faster and faster as the crystals cool down and reform.
So that's turning from liquid into crystals
That's
again.
right.
Oh, that's beautiful. Look at that. That's lovely.
Not so long ago, these things were all the rage. They're called anaglyphs. That's just a posh name for a three-dimensional picture. Now, there's actually two pictures here, one in magenta and the other in green, and they're printed one on top of the other. Now, for the rest of this section, you need to make a pair of glasses like this. Snazzy, aren't they, eh? You see, the magenta picture shows at best through the green filter, and the green picture shows at best through the magenta filter. This means the magenta and green filters make sure that each of the two pictures go to the correct eye. Now, instead of these rather wonderful glasses, you can just as easily hold up two bits of coloured filter, cut from large sheets of coloured plastic like this. There you go, magenta colour and a green colour. Now, if you want to be really accurate, this magenta coloured one has a Lee number 113, and the green colour has a Lee number of 124. And when you're cutting it out, cut from the edge of the corner, don't cut into the middle, it wastes the stuff. There you are. Don't worry about the Lee numbers, any colours that are close will do. Right, now hold them in front of your eyes, like that, okay? And make sure the magenta one is on your left-hand side and the green is on the right-hand side. In fact, if you know anything about ships, it's the same as port and starboard colours. There. Right, with your filters in front of your eyes, have a look at the poster again. You may have to adjust your TV a bit to get the effect working. OK, take your glasses off. It's interesting to explore why having two eyes gives us three-dimensional or stereo vision and whether it's of any use to us. Now, it's quite easy to do. Here are two lamps. The gap between them is about the same as the gap between our eyes. In front of this one is a magenta filter, and in front of this one is a green filter. Now, they shine onto the screen over there. We've set up a camera looking at the other side of the screen so that you can't see what I'm doing. Now, what do you think this is a shadow of? This shadow is cast by the green lamp, but you could also just use the magenta one. But by using only one of the lamps, it's like the object with one eye. OK, now put your glasses back on and see if you can tell what it is when I switch both lamps on. There they go. Now, it's like you're looking at the object with two eyes. Each lamp casts a separate shadow. The filters make sure only one shadow goes to each eye. OK, if you look at it for real, it's a model molecule. But look at the different effects as I start moving it about a bit. There we go. You may take a bit of time to get used to the effect. And it's a bit sad, but unfortunately, it doesn't actually work for everybody. I personally found it didn't work for me at first, but if you look away and roll your eyes about a bit and then suddenly look back, all of a sudden it worked for me and it was great. Right, look at something else. Let me just move that out of the way a second. Which way do you think my hand is moving? Towards you or away from you? The key to why our eyes gives us stereo vision is here. Now remember, they're separated by about 5 centimetres. The experiment's quite simple to do. Try to find out what happens when you move the two lamps apart and be prepared for this amazing effect.